Number one, the students investigate the variations with temperature theta of the resistance R of a copper wire. The plastic cover copper wire is wrapped around a mercury in glass thermometer and immersed in a beaker of water. This is a diagram. The students allow the water to cool slowly from 95 degrees Celsius. The students measure the resistance of the wire and the temperature of the water at the same instant. The results are shown with error bars for R. Errors in theta can be ignored. Okay. Question. The student suggests that R is given by R equal R0 times 1 plus alpha theta. Draw a line of best fit for this data that is consistent with these equations. It's consistent based on this statement. Consistent, it means a straight line. So to create the graph, we are connecting this initial point to the final point. Actually, like this, something all, and will be like this. Okay. Next question. Calculate the gradient of your best fit line. Okay, the gradient we can gain through delta R over delta theta. Delta R you can find through this point. This point is 7.9. So to this theta and to this point. Okay, so 7.9 minus this is 6.3 here. 7.9 is 6.3. So 7.9 minus 6.3, and then here is 96, is 96, and this is 21. 96 and this is 21. So we can gain the gradient 7.9 minus 6.3 over 96 minus 21, 1.6 over 75, 0.0213 ohms. You use alpha, state an appropriate unit for alpha. Okay, so R0 is 6.3 ohm. You can see on the graph. So alpha equal gradient over R0 over this one, this number. The gradient is 0.02133 ohms over 6.3 ohms as well. And the result is 0.0033862 degrees Celsius. This one. Okay. Or it is 2, 3.3862 times 10 to the power minus 3 degrees Celsius, or 3.4 times 10 to the power minus 3 degrees Celsius. Next question. Number 2, a small ball is released from rest at time equals 0 in front of a vertical ruler. A multi-flash photograph is taken of the ball at equals 0 and every 0.05 seconds from then on. Okay, let's release position the first position when t equals 0. The distance as fallen by the ball is related to the acceleration g of the ball and t by s equal 1/2 gt squared. That means g using the photograph. When you look uh, this ruler, this point, 1, 3, I'm gonna using when t equals 0. This is 0.054, so it means this is when is t equals 0, so the second is this is when t equals 0.050, okay? And this one when t equal is when t equal 2 times 0.050, okay, and so on. But I would like to using when t equal 0.050 to calculate g. Yeah. Okay. Okay. So based on this information that s equal 1/2 gt squared, so it means g equal, we can rearrange this formula becomes 2s over 2s over t squared. So it means g equal if t equal 0.050, so g equal 2 times 1.2. 1.2 because you look, this is 1.2 is one. This is 1.2. Okay. From this one to here is 1.2. The distance is 1.2 from this one from 5 to 6.2 here. Okay. So the distance is 1.2 over t squared is 0.050 squared. Okay. And if you calculate, the result is 960 centimeters s squared. Okay, centimeter over s squared, centimeter per second squared. Next question. The percentage uncertainty in T is 5%. Estimate the absolute uncertainty in your value of G. From part A, we have information that they arrange the formula that G equals 2S over T squared. The uncertainty in G depends on the uncertainty in T. Okay, so we can use the formula for the uncertainty propagation like this one, delta G over G equal to delta T over T. Okay. Uh, from part A, we have information that G equal 960 centimeter per second squared. Right. So it means delta G over G equal 2 times, based on this information, 2 times 5%, and the result is 0.10. This is delta G over G equal, it's 0.10. So it means delta G equal 0.10 times G times 1, 0.10 times 960 centimeter per second squared. And if you calculate, the result is 96 centimeter per second squared. So the value of G with its uncertainty is G equal 960 plus minus 96 centimeter per second squared. Next question. C. Suggest a suitable value for the maximum durations of the flash. We want the ball travel a distance no greater than the uncertainty in position during the flash. So we can determine the maximum flash duration through the formula delta delta S equal V times delta T maximum. Delta meaning change, the change. So the change of T maximum, delta T maximum, equal delta S over V. Okay. And after that, the uncertainty in positions between delta T, wait, I have to write in here that, sorry, delta S equal 1 millimeters. 1 millimeters is convert to meters becomes becomes 0.001 meters. Yeah, correct. 1/1, yeah, correct. 1/1000. So it means delta T maximum equal 0.001 meters over 2 meters per second. And the result is 0.0005, it's 1 second. Okay. 0.005 second is 1 over 2000 second. This one. Number 3. We transmit a radio signal to Q. Relative to the Earth's surface, Q is stationary and P moves at a speed of 0.70 c as shown in this diagram. Right. State using Galilean relativity the speed of the radio signal relative to Q. Okay, so we can determine the speed using the Galilean velocity addition formula that phi, okay, phi signal relative Q, phi signal relative Q equals phi signal relative P plus phi P. So it is equal C plus 0.70 c. C is the speed of the radio signal relative to P, which is C. Yeah. So it becomes if 1c plus 0.70c equal 1.70c, this one. Okay. So Vpc is the speed of the radio signal relative to P, while Vp is the speed of P relative to Q. This one. Next. So the speed of the radio signal relative to Q is this one, 1.70 t. Okay. Determine using relativistic velocity addition the speed of the radio signal relative to Q. We need to using the relativistic velocity addition formula that instead that U equal Ux and plus P over P is Vp 1 plus Ux and phi over C squared. This one we are going to use in this. Okay, so U equal Ux is C plus 0.70 C. It is 1 plus C times 0.70 C over C squared. C times C is C squared. So comes like this. Comes 1.070 C over 1 plus 0.70. So it's going to be 1.70 C over 1.70. It is equal 1 if divided. So the result is C. A paradigm shift in science replaced Galilean relativity with the theory of special relativity. Explain how this paradigm shift was linked to Maxwell's discovery of a set of electromagnetic equations. I have provided my answer about this question. So, number 4, the space-time diagram X, CT for a space station as shows the world lines of two clocks, clock 1 and clock 2. Its clock is 2.0 kilometers from S. The space-time diagram also shows the world line of spaceship A. This is the spaceship A line. And this is clock 1 and this is clock 2. So space A and clock 1 has intersection at here. Okay, 2,8. The question. Outline how clock 1 and clock 2 can be synchronized with a clock on S. I have provided my answer for this question. Let's continue. Determine, in terms of C, the speed of A in the reference frame of S. Okay. So if you look at this diagram, I would like to discuss about this diagram. The intersection here, so this is the distance is 8, okay, this is 8, and if theta here, okay, and this if this is this information, this is x, okay, so tangent theta, this is this angle theta, tangent theta actually equal, this is 2 over 8 or 1/4. Also tangent theta we can state as tangent theta as the about the axis is x over, this is axis for CT, this is axis, the horizontally is x, the vertically is x, is CT, so this is CT. All right, so let's continue discuss here. CT equals C times T, okay, or T equal CT over C. And we're going to using the speed equal x over t. It is x over, based on this information, ct over c. And it is over x over ct times c here. Okay. As you know that from the previous explanation that I have explained that ct that x over ct equal tangent theta. Okay, tangent theta times c. Tangent theta is 1/4. So 1/4 times c is what? Or 1/4 c or c quarter. Next question. Clock 1 and clock 2 emit separate like signals when A is at 0,0 at origin. Identify on the diagram the proper time that elapses between the arrival of the like signals at A. Okay, again on this diagram, we're going to discuss about this. Okay, I'm gonna clean first. Right. Clock 1 is at here, 2 kilometers. Clock 2 at here, minus 2 kilometers. So positions at time t we can determine through Vt or xt. You can using xt also. 1 1/4 C based on this information just now. So that's one. On part two, times T. Okay, if we see when T equal 8, when T equal 8, it means V8 equal uh, 1/4 C times 8. So it's going to be 2C. Okay. So to see the position here, okay. So we are going to connecting. I will sketch using this color. Okay. Okay. On and a different color from two to this point. Okay. And this one. Okay. Okay. So this is the proper time. Next question. At even E spaceship P leaves S to intercept space A. The speed of P is 0.50 c in the reference frame of S. Identify with the letter X on the diagram the event of P intercepting A. Okay. So if we are going to find, okay, on this diagram, based on the information that Vp equals 0.5 c. It means that the gradient is 0.5, or we can, I'm going using this one, tangent theta p, the gradient, ct over x. So c over vp, okay? So it's going to be c over 0.5 c based on the information, okay? 1 over 0.5, or it is 2. So if gradient 2, right? If gradient 2, if gradient or m equal 2, so x equal 2. If x equal 2, so ct over 2 equal 2 and ct equal 4. So the coordinate point becomes 2, 8. 2, 8 here at the intersection here. Okay, so the line here. I'm going to sketch the straight line. This is straight line. You can sketch your own straight line as well. Okay. Let's continue to the next question. State in seconds the time of event x for 4 clock 2. Okay. So 8 kilometers I will convert becomes meters. 8,000 meters. So T equal S over C, or it equal 8,000 meters over 3 times 10 power 8. Okay. C is speed of light, 3 times 10 power 8 meter per second. So if you calculate, the result is 2.7 times 10 power minus 5 second. Next question. Spaceship A then returns to S. The space-time diagram shows the rest frame of A on its outward journey, x action, ct action, and on its return journey, x double action and ct double action. The question: an observer in A determines for the reference frame of S the time t1 immediately before the change of velocity of A and the time t2 immediately after the change of velocity of A. Identify with lines and labels on the space-time diagram the difference between t1 and t2. Right. So T1 is T1 is parallel with X axis. It's okay. Okay, it's T1 here, T1 line. While T2, wait, T2 line parallel with one or continue with X double accent. Okay, it's one. Sorry. This is T2. So this is the delta T. Okay. The difference, delta T. Next question. Explain how the distance between T1 and T2 arises. I have provided my explanation. Question number 5. Means are formed in the Earth's atmosphere 2.5 kilometers above the surface and then travel vertically downwards at a speed 0.975 c. C is speed of light. The mean lifetime of a muon is 2.2 mu(s) when measured in a frame in which the muon is at rest. Calculate the mean lifetime of the muon for the reference frame of the Earth. This is delta S, delta T, sorry, this one. Okay. And the speed is 1 v is 0.975 c. So I would like to using the formula for time dilation delta t action equal delta t over square root 1 minus v squared over c squared. So this is 2.2 mu(s) microsecond. 1 minus 0.975 c squared over c squared. C squared equal 1. So 2.2 mu(s) over 1 minus 0.975 squared comes 2.2 mu(s) over 0.049375. If you calculate the result is 9.91 mu(s). Next question. Muons are detected at the Earth's surface. Explain with supporting calculations why this is evidence for time dilation. To calculate the time taken to reach the Earth as measured in Earth frame, we need to using this formula that T equal D over V. Okay. Distance from 2.5 kilometers, I mean. 2.5 kilometers becomes 2,500 meters. Okay. And the speed of muons Speed of muons is 0.975 C, based on information on part A. So it's going to be 2,500 over 0.975 times 3. Sorry, this is 3 times 10 power 8 C. Okay. Okay. This is C is speed of light. It's going to be 8.5 times 10 power minus 6 S equal 8.5 mu S. And after that, we're going to find the time dilation reaction equal gamma times tau zero. Uh, it's going to be 1 over square root 1 minus v squared over c squared times uh, tau zero. Okay, and then it's going to be, this is 2.2. Okay, 2.2 mu s, so it's going to be 2.2 over square root 1 minus, from our previous calculation, this is 0.975 squared. And it becomes 2.2 over square root 0.0494. And the result is 2.2 over 0.222 becomes 9.9 millisecond. And for my explanation, my brief explanations I have provided. Okay. Let's continue to the next question, number 6. A fly a flywheel is a rotating cylinder used to store rotational kinetic energy. Energy can be transferred from the flywheel as it slows down. This is a diagram. A flywheel used to store energy has a moment of inertia 0.072 kilograms per meter squared and a maximum angular speed omega of 8,400 radian per second. Question. The rotational speed of flywheel is reduced uniformly from the maximum speed to 3,600 radian per second in a time of 9.6 seconds. Show that an average power of about 200 kilowatts is transferred from the flywheel as its speed is reduced. Okay. I will using the formula that delta E change in energy equal 1/2 times I times omega I. Omega I is initial angular speed squared minus omega f squared. Omega f is final angular speed. It's going to be 1/2 times 0.072 times 8,400 squared minus 3,600 squared. And if you calculate the result is here, the result is 2,073,600 joule. And the average power, sorry, the average power average power or P equal delta E over delta T. We have 2,073,600 73,600 over 9.6 equal 216,000 watts, or convert to kilowatts becomes 216 kilowatts. After that, calculate the torque acting on the flywheel as it decelerates. The torque to calculate the torque acting on the flywheel during deceleration, we can use the relationship between power, torque, and angular speed. And the formula like this, that power equal uh, torque times the angular speed. So it means torque equal power over the angular speed. Uh, I would like to find the angular speed average. Angular speed average is initial angular speed plus the final angular speed over 2 equal 8,400 plus 3,600 over 2. This is 6,000 radian per second. So torque equal 2.16 times 10 power 5 over 6,000 equal 36. The unit is Newton meters. Calculate the number of revolutions that the flywheel makes as it slows down. Okay. Right. For these problems, I would like to using the formula. The formula theta equal the uh, angular speed average times t. Okay. So we calculate this is the angular speed average. One 6,000 times t equal, sorry, 6,000 times t is 9.6. Okay. And the result is 57,600 radians. Yeah. And we are going to convert this number in radians, uh, convert to revolution. So number of revolution equal theta over 2 pi. Okay. It means 57,600 over 6.2832, goes 2 times pi. And the result is 9,170 revolution. Next question, an engineer changes the flywheel design to increase the maximum energy that it can store. Identify two factors that the engineer can change to do this. I have provided my answer about this. Next question. A fixed mass of an ideal gas is taken through a cycle that consists of three processes. X to Y, isothermal compression from a pressure of 0.1 MPa M Pascal and volume of 1.2 times 10 power minus 3 m cubed to a pressure of 0.48 m Pascal. Isobaric expansion at y to z, x to x, adiabatic expansion to the initial state. Draw on the axis the PV diagram for the cycle x and y are plotted for you. Numbers are not required on the axis. We're going to sketch draw this diagram based on this information. First, X to Y is isothermal compressions. It means the implication curve inward from X to Y. X to Y is, sorry, okay, okay. And after that, from Y to Z is isobaric expansion. So it is the horizontal line from Y to Z. Y to Z, it means here, the horizontal line, this is Z. And after that, from Z to X, Z to X, adiabatic expansion to the initial state, it means going to the X from Z to X to the initial state. That is the arrows to downwards. Next question. Show that the volume of the gas at Y is 0.25 times 10 power minus 3 m cubed for an isothermal process. The ideal gas law gives us that Px times Vx equal Py times Vy. We are going to find Vy, so we need to rearrange this formula becomes Vy is the subject. If Vy is the subject, the formula becomes like this. Px Vx over Py. It's going to be 1.0 times 10 power 5 times 1.20 times 10 power minus 3 over pressure in Y is 4.8 times 10 power 5. 1. And if you calculate, the result is 0.25 times 10 power minus 3 and cube, meters cube, because volume. Next question. An algebraic statement of the first law of thermodynamics is Q equal delta U plus W. Data for the cycle are provided in the table, in this table. Complete. The table use the answer box below for your calculation. First, the process X to Y. Process X to Y. Work is 1 minus 188. This is work. And uh, isothermal or delta U here, delta U equal 0. Okay, here 0. Right. So because internal energy depends on the temperature, which is constant in an isothermal process. So it means we can determine Q based on the formula delta U plus W equals 0, 0 plus minus 188, or minus 188, 188, 188 here. Now, Y2C, okay, Y2C, we are going to determine delta U. Q is 1, 262, and W is 105. So delta U equal Q minus W, 262 minus 105. It is 157 joule, 157 joule. And after that, Z to X. Z to X W is 157, and this is a return to the original state based on the graph on uh, the previous question and solution. So it means for full cycle at delta U equal minus 0 plus 157, and it is minus 157. So here minus 157. And for Q is delta U plus W equal minus 157 plus 157, it equals 0. So here is 0. And for whole cycle, we need to calculate the accumulation of Q minus 188 plus 262 is 74. Okay. And the accumulations of delta U is 0 because 0 plus 157 minus 157 equal 0. I think that is clear. Let's continue to the next question. Determine the volume of the gas at C. We are going to use the work formula for isobaric expansion Y to C. Y to C. Right. So W equal P times delta phi equal P times volume in Z minus volume at Y. Okay. So volume, if we will find volume at C, if VC becomes the subject, we have to rearrange this formula. Becomes like this: Vz equal W over P plus Vy. So Vc equal 105 over 4.8 times 10 power 5 plus 0.25 times 10 power minus 3. And if you calculate, the result will be 2.1875 times 10 power minus 4 plus 0.25 times 10 power minus 3. And the result is 4.6875 times 10 power minus 4 m cubed. Or it's going to be 0.47. Okay, 7 times 10 power minus 3. From power minus 4 becomes power minus 3. M cubed, the result. This is the volume at Z. Next question. Determine the efficiency of this cycle. The efficiency of a heat engine, the formula is like this: the efficiency eta over W net over Q inside K. So it's going to be 74 over 262 times 100%, sorry, because efficiency in percentage. It becomes 0.2824. 100%. It is 24% or 28%. Wow. Outline why this theoretical cycle is unsuitable for use in a practical heat engine. I have provided my answer for this question. Number 8. A real image 4 times larger than object. It means based on this information m equal 4. Its form 0.40 meters from a converging lens. Calculate the focal length of the lens. M equal V over U. And based on this information that M equal 4. So it means it is equal 4. So U equal V over 4, V quarter. And we will using minor equations or length formula 1 over F, 1 over V plus 1 over U. So it is 1 over V plus 1 over V over 4 because U equal V over 4. So it's going to be, 1 over V, 1 over V plus 4 over V. So it becomes 5 over V, like that. So if this is 1 over F, so 1 over F equal 5 over V. So it means F equal V over 5. V is 40, okay, because 0.4 meters, it is 40 centimeters, like that. So 40 over 5 equal 8.0 centimeters. The converging lens is replaced by a diverging lens of focal length f. The positions of the object is shown, like on this diagram. Determine using a right diagram the nature of the image formed. Okay, we are going to sketch first, and I would like to using the different color for this one. So the ray goes to here, and then from this focal length, reflect to there, and after that, the different rays through this point, the center, okay, and through here, and of F here, and the image here. It's the image. And the nature of the image form, so virtual, upright, and diminished. Identify the optical components in an astronomical reflecting telescope with Newtonian mounting. I have provided my answer for this one. Okay, let's continue. Explain one advantage that an astronomical reflecting telescope with a Cassegrain mounting has over one with a Newtonian mounting. So let's continue. In a reflecting telescope with a Cassegrain mounting, the primary mirror has a focal length of 8.0 meters. The telescope is used to view a feature on the moon that subtends an angle of 2.5 milliradians at the axis of the primary mirror. Question. Calculate the height of the image formed by the primary mirror. So I will using the formula H equal F times theta, which F is 8.0 meters, while theta. Theta is 2.5 milliradians. It means 2.5 times 10 power minus 3 radians. So it becomes 0.8 times 2.5 times 10 power minus 3. And if you calculate, the result is 20 times 10 power minus 3, or 2.0 times 10 minus 10 power minus 2 meters. Next question. The initial paths of two rays parallel to the principal axis are shown on the diagram. Show by completing the paths of these rays the formation of the final image at X. Have it is different color. X is eyepiece. Okay, eyepiece 1. So the ray, this ray to the primary mirror, after that reflect to the principal axis as well. This ray, straight line to primary mirror and to the secondary mirror, and from secondary mirror reflecting to the eyepiece. Okay. Okay, these are the strike line. Let's continue. The secondary mirror is 4.5 meters from X. From X, calculate the focal length of the secondary mirror. I would like to find U first. U equal 4.5 minus 8, and it is 3.5. And we're going to using mirror equations or lens formula. That's 1 over F equal 1 over phi plus 1 over U, or 1 over F equal 1 over 4.5 minus 1 over 3.5, or 3.5 minus 4.5 over 15.75. So it's going to be minus 1 over 15.75. This is 1 over F. So 1 over F equals 1, this fraction, minus 1 over 15.75. And we're going to find F. So F equal, the opposite of this fraction is minus 15.75 over 1, or minus 15.8, and the unit is meters. Number 10. Like propagates along an optic fiber that has a core of refractive index 1.59 and a cladding of refractive index 1.48, show that the critical angle at the core cladding boundary is approximately 70 degrees. All right. We use Snell's law at the boundary where total internal reflection occurs. And the equation is n core times sine, I would like to using delta C, n core times delta C equal n cladding times sine 90. Okay. If you're going to find sine theta C, because we will find theta C. So if sine theta C becomes the subject, this equation becomes n cladding, equal, I would like to substitute the number 1.48 times sine 90 is 1 over n core is 1.59 according to this information. And this equal, this result is 0.9308. So it means theta c equal arc sine or sine to the power minus 1 of 0.9308 equals 68.6 degrees or 69 degrees. This number is approximately 70. Okay. A ray enters the optic fiber from the air through a core surface that is at 90 degrees to the axis of the fiber. So actually, this is the fiber inside the cylinder. Determine the largest angle of incidence I that this ray can have in the air for total internal reflection to occur at the core cladding boundary. The critical angle or theta c equal 68.6 degrees from part A. Since light travels along the axis, the internal angle or R with the axis must be less than or equal to R 90 minus theta c. It means 90 degrees minus 1, 68.6 degrees. And the result is 21.4 degrees. After that, we're going to apply Snell's law and air times sine I equal n core times sine R. If we're going to find sine I, so sine I becomes the subject, is n core times sine R divided by n air. So n core times sine R is 1.59. This is n core. Sine 21.4 over n air is 1.00. And if you calculate, the result is 0.5798. So it means we can determine I equal sine to the power minus 1 of this number, 0.5798 equal 65.5 degrees. So 35.5 degrees is the largest angle of incidence. Okay. Let's continue to the next question. Describe what happens to rays of light with angles of incidence greater than I. I have provided my answer for this question. Next question. See, the attenuations per unit length in the core material is 5.5 decibel per kilometer. Estimate the length of the optic fiber that will reduce the brightness of light by a factor of 10 power 6. Okay. Attenuation equal is attenuation equal 10 times log 10 of 10 power 6. And based on logarithm rule, we can write this term becomes 10 times 6 log 10 of 10. Log 10 of 10 equal 1. So the calculation becomes 10 times 6 times 1 equals 60. So attenuation equal 60 decibel, the unit. And we're going to find length. Length equal 60 attenuations over this one of 5.5. And the result is 10.91 kilometers or 11 kilometers. So next question, number 11. Outline the differences between open stellar clusters and global stellar clusters. Open stellar clusters and globular stellar clusters. I have provided my answer for this question, this one. You may copy or you may add something into this explanation. B. Discuss how Cepheid variable stars are used for distance determinations in astronomy. As well, for this question, I have provided my explanation. The next question, galactic dust absorbs light. Predict the effect that galactic dust has on the estimate of the distance to a Cepheid variable star. For each one, I have provided my explanation. Number 12. Data for the main sequence star, 10 letters they are provided. T, the sun, and L, the sun refers to the temperature of the sun and the luminosity of the sun. Surface temperature of 10 letter T is 6.3 of temperature of the sun. Luminosity of 10 letter T is 100,000 luminosity of the sun. Calculate the comparison or the ratio radius of 10 letter T over radius of the sun. I will using Stefan Boltzmann law. The law is, I would like to writing as 4 pi r squared or sigma t over 4. And because it's comparison, I would like to write in the comparison becomes L of 10 laser T over L or luminosity of the sun, R10 laser T over R of the sun squared times temperature 10 laser T over temperature of the sun, power 4. Okay. So we need to find this one, this comparison, R10 laser T over R of the sun. So I would like to rearrange this equation becomes R 10 letter T over R of the sun squared equal. This is the value is 100,000 based on the information, and this is the value of 6.3 on the information. So R10 letter T over R of the sun equals square root of, if you calculate this, the result is 63.47 and it is 7.97 or 8.0. Show that the mass of 10 letter T is about 30 times the mass of the sun. I will be using the mass luminosity relation for main sequence stars. So L over L of the sun equal M over M of the sun is mass power 3.5. Okay, this is the result. The value is 100,000. So you can writing that M over M of the sun to the power 3.5 equal 100,000, or m over m of the sun equal 100,000 to the power 1 over 3.5. And if you calculate, the result is 26.8, or based on this information, approximate becomes actually 27. But I would like to approximate becomes 30, because 30 times the mass of the sun. Outline with reference to its mass, the like final of 10 letter T. I have provided my answer for this question. Next question. The galaxy NGC 2651 is 350 million light years, and LY is simply of million light years from Earth and has a redshift 0.025. Show that the NGC 6251 data lead to an estimate for the Hubble constant of about 70 kilometers per second per MPC, okay, megaparsec, this one. So the first step, I will convert distance to megaparsec. So distance equal 350 times 350, one MPC the previous, I have to convert MPC to light years. One MPC equal 3.26 times 6 times 10 power 6 light year. This is for 1 megaparsec. So distance equal 350 times 10 power 6 light year over 3.26 times 10 power 6 light year, and the result is 107.4 megaparsec, like this. And then after that, estimate the recessional velocity using the redshift. So phi equal z times c is 0.025 times 3 times 10 power 5 kilometer per second. If meter per second, this is 10 power 8, but I have converted it becomes kilometer per second, so this is 10 power 5. And if you calculate, the result is 7,500 kilometer per second. So we're going to estimate the Hubble constant. Hubble constant is H0. This is Hubble constant, simply H0. So H0 equal phi over D. It's been 7,500 over 107.4 megaparsec. And the result is 69.9, or it is 70 kilometer per second per megaparsec. That is. Next question. Estimate using your answer to part A to the age of the universe in second. The age of the universe in a second. So I would like to convert megaparsec becomes kilometers, megaparsec, MPC to kilometers. All right. 1 megaparsec equal 3 times 3.086 times 10 power 19 kilometers. So it means H0, or the Hubble constant, equal 69.9 over 3.086 times 10 power 19. And the result is 2.27. times 10 power minus 18 per second. Then we can find the age of universe is 1 over h0, 1 over the Hubble constant equal 1 over 2.27 times 10 power minus 18. And the result is 4.41 times 10 to the power 17 second. State the assumption you made in your estimate for part B1. This is my assumption.